Hello, my name is Lucas and I'm going to present deep learning-based framework for shape instance registration on 3D CAD models. So CAD systems are widely used throughout the life cycle of engineering projects. Alongside with the BIM methodology, they can improve the quality and reduce the costs of several tasks such as construction, maintenance, and operation. These systems relies on 3D CAD models, which the complexity grow by the year, posing challenges to efficient storage, transmission, and handling. These CAD models are composed by several connected components which are represented by similar triangular meshes, which only differ by an affine transformation. And these instance information are not inside the 3D CAD model. In 2013, Iveson and Salles reduced the 3D CAD model complexity by removing this redundant information, computing an affine transformation that can be used to instantiate several connected components using the same triangular mesh, but it heavily depends on vertex ordering and topology. Several techniques, which some are deep learning based, perform shape registration and point cloud registration, but they are not well suited for the 3D CAD domain, since their outputs free-form deformation grids, which are not very good for rendering tasks. They also output rigid body and similarity transformations, but connected components may differ for non-uniform scaling. And they also use parametric surfaces, such as cylinder and cones. But during the modeling, general triangular meshes are often used. In 2010, Duerol extended the ICP algorithm, introducing the scale matrices directly into the minimization step and computing an affine transformation to perform point cloud registration. This method is well suited for the 3D CAD domain, but as we see further in the presentation, we were able to develop a technique to registrate this point cloud with an affine transformation that can produce more consistent results. Inspired by this recent work, we proposed a deep learning-based framework to remove this redundant information of similar triangle meshes by identifying a geometry type using the .NET++, then computing an optimal affine transformation to perform this registration. Our method is independent of vertex ordering and surface triangulation by relying on point clouds. And during the optimization step, we guarantee an upper bound on any surface errors. So the framework. The framework takes as inputs a triangle mesh and then perform a normalization step. After that, we can sample a uniform point cloud on the surface, and this point cloud is used as input on the .NET++ to obtain the base type, which has a reference mesh associated. This reference mesh, alongside with the normalized triangle mesh, is used in the instance registration step to obtain an affine transformation that can instantiate the input triangle mesh using the base type reference mesh. In the preprocessing stage, we first perform a normalization step, in which we center the mesh as the origin. We then align the mesh with the 3D axis using the principal component analysis, and then we scale the mesh into the interval of -half and half. After that, we sample a uniform point cloud using the method proposed by Osada et al., which guarantees a uniform point cloud since the probability of each point belonging into a triangle is proportional to the triangle area. After sampling the point cloud, it is used to identify which base geometry type it is using the .NET++. This base geometry type has a reference mesh associated, which later can be used to simplify the model. After classifying, we enter the instance registration step, which our goal is to obtain a matrix that can transform a source mesh into a target mesh, which the source mesh is the reference mesh associated with the base geometry type, and the target mesh is the normalized input triangle mesh. During this stage, we compute the surface error, which consists of the distance of the point cloud centered on the target mesh for the source mesh multiplied by this matrix M. This sum is then divided by the number of points on the target mesh. In the beginning of the optimization procedure, we first check if the surface area is already smaller than a threshold alpha 1. If so, we set M to identity and proceed to the next geometry. If not, we compute the PCA for both the source mesh and target mesh and combine them to initialize M. Using this initialization, we were able to obtain better results. This is further discussed on the paper. After that, we start the outer loop, which the main goal is to interrupt the optimization when the upper bound is reached. It also updates the point cloud densities, which is required to obtain better registration, and it maintains the point cloud of the source uniform when transformed by the current matrix M. In the inner loop, inspired by the point-to-mesh work published by Hanoka in 2020, we developed a method using the add and optimizing using the chamfer distance as a cost function to update the matrix M using the point cloud sampler on the outer loop. If the chamfer distance stops decreasing for a number of iterations, we stop this inner loop and increment the density of the points. This number of iterations is used as a heuristic to identify if the optimization procedure is stopped converging. Then we update the point cloud densities to continue improving our registration. At the end, we see if the surface error is greater than a threshold alpha 2. If so, we discard this instance and use the triangle mesh as itself in the model. If not, we combine M with the denormalization transformations and obtain a final instantiation matrix, which is used to instantiate the component using the reference mesh. At the end, we have a model that is composed by triangular meshes that we are not able to optimize, and the reference meshes alongside with several instantiation matrices to instantiate the desired connected components. This verification step is required to avoid misclassification errors. Then we perform some experiments. We mostly experiment on the CAD model, which is composed by 1800 geometries, labeled in 16 geometry types, as described in the figure. During the training of the .NET++, we have to balance the dataset, since the base types are very unbalanced. Using this data augmentation balancing, which we take the point cloud and additionally perform uniform scaling and other random translations and rotations, balancing the dataset, we were able to obtain an accuracy of 99.98% and an F1 score of 1 for many geometry types. In the worst case, a F1 score of 0.9921. The accuracy as close to 100% is better, and the F1 score as close to 1 is the best. After training the .NET++, we fine-tune the parameters, and mostly we set the first threshold as the optimization goal for 0.001 and the acceptance threshold at 0.005. Using these parameters, we were able to obtain a mean surface area of 0.003 and a standard deviation of 0.00909. These results shows that we could obtain a model which has a very good quality, and we, using these parameters, we were able to reduce the model to almost 2% of the original size. For comparison, we We also optimized the model using the method proposed by Ilson and Salles, and we showed that our optimization obtained a very close result to theirs. However, during the modeling, these geometries can be modeled using different ways and by different people using different software. And these triangle meshes can have different triangulations and topology. To simulate this case, we shuffled the vertex and the triangulation of the geometries, and we shows that our method is to maintain the same memory reduction, while Ibsen and Salles cannot optimize this type of model, since it's very topology dependent. After that, we performed a series of experiments using different techniques for optimizing the model. In the first one, we used just the SICP algorithm, and in the second one, we use our loops integrated with the SICP algorithm. In the third one, we use the add-on optimizer with the chamfer distance x-cost function without our loops. And in the last one, we shows our proposed solution. We can see that our proposed solution outperformed the average time in each one of the other methods. But it is still costly, which shows the importance of using the .NET++ to pick one geometry type, so we can optimize just for this one. We also can see that using a more relaxed acceptance threshold, we obtain very similar results of memory reductions for all the methods. But when we use a more rigorous one, we still will see that our method still produces a very good memory reduction, while the other starts to perform more poorly. After that, we use the same trained .NET++ and in our framework to optimize a model with 74,000 unlabeled geometries, and obtain a mean source error that was not as good as we found on the previous model, and also a memory reduction of only 64%. These results are directly related to the lack of similarity from the base geometry types compared to the geometry types found on this model. For example, we see a rectangular torus that was identified as a circular torus, but this geometry was discarded during the optimization step. And since we don't have a rectangular torus in a basis type, geometry types, these geometries were not optimized and simplified into one reference mesh combined with several matrices. This shows the importance of previous knowledge of the geometry types that will be found on the model. We present the shape instance registration framework, which obtains a significant memory reductions on CAD models by relying on .NET++ and add optimizing using chamfer distance x-cost function, and overcome major drawbacks from previous works. As future work, we intend to investigate the use of clustering techniques to avoid the necessity of previous knowledge of the model, apply the framework to other CAD models, and use the framework in more general scenarios, such as scanning 3D point clouds. Thank you for watching.